Hi everyone, welcome back. In this video, we will have a brief discussion regarding the motion in a plane, that is two dimensions, and then we'll also discuss about the projectile motion. Okay, so uh, the same physical quantities that we have discussed in the previous chapter, we will be using them in the discussion here as well, but we will use those physical quantities in order to understand the motion of the body in two dimensions, that is in a plane. Okay, so in the previous lecture we have discussed briefly about the vectors. Okay, now before we proceed further, let's define something called a position vector. So earlier when we were discussing about motion in a plane, we discussed about position. So what's position vector? So it's a vector basically which gives us the position of a particle with respect to a reference position, which will be taking as origin most of the times. So suppose, let's say a particle is moving in xy plane. Okay, let's say at some particular instant of time its coordinates are given by x1 comma y1. Then what is its position vector? This is its position vector. Okay, this is the position vector of that particle at that instant of time. We can write it as r1 bar is equal to x1 I cap plus y1 j cap. Let's say if it was moving, let's say after some instant of time, it was at another point whose coordinates are given by x2 comma y2. Then its position vector, let's say it's represented by r2 bar, then r2 bar can be written as x2 I cap plus y2 j cap. Then the displacement of the body when it goes from this original point, let me call it A, to the point B after certain amount of time. During that interval of time, this would be the displacement of the particle. Displacement of the particle is basically the change in position. So we can write it as x2 minus x1 I cap plus y2 minus y1 j cap. So this would be the displacement of the body. So you have understood the position vector. Okay, the same way we can define the position vector of a particle if it's moving in 3D space. Suppose, let's say, for particle the coordinates of its position are given by, let's say, something like x comma y comma z, then its position vector, generally I represent the position vector with r bar. We can write it as x I cap plus y j cap plus z k cap. Okay, now this is what position vector is. So using the point of position vector, let's continue with the discussion. Okay, so let's say a particle is moving in 3D space. So using the discussion for the 3D space, we will use whatever we get from this discussion. We'll be trying to understand motion of a body in a plane. Let's say a particle is moving such that its position keeps changing. Let's say at this instant of time, the coordinates of position are given by xi cap plus yj cap plus zk cap. So if it's moving, okay, any one of the coordinates must definitely be changing with time. Okay, either x or y or z, or any two of them, or all the three of them might be changing with time. Then it is said to be in motion. If all the three coordinates do not change, if all three x, y, z remain the same with respect to time, then that particular particle is said to be at rest. It's not in motion. Okay, then if this is the position vector, as we have discussed earlier, the velocity, basically we write the rate of change of position. So we can write it as d by dt of xi cap plus yj cap plus zk cap. So we can write it mathematically, d by dt of x into I cap plus d by dt of y into j cap plus d by dt of z into k cap. So here d by dt of x would be the rate at which its x coordinate changes, or the rate at which it undergoes displacement along x-axis, so which would basically be the x component of velocity of that particular particle. So where Vx is its x component of velocity, which is given by d by dt of x. Then its y component of velocity is given by d by dt of y plus Vy into j cap plus Vz into k cap similarly. Okay. So the velocity V bar is Vx I cap plus Vy j cap plus Vz k cap. So if you look at Vx, it only depends on how the x coordinate of that particular particle changes. So x component of velocity depends only on its x coordinates of its position and how it's changing. So x component of velocity is not dependent on the motion corresponding to, motion parallel to the y-axis, or the x component of velocity does not depend on the y coordinate of that particular particle's position. Okay, so once we get the velocity, we differentiate it further. Once again, we would get acceleration. So we can write acceleration as d by dt of v bar. So we can write d by dt of vx I cap plus vy j cap plus vz k cap. So again, we can write it mathematically as separately d by dt of vx I cap plus d by dt of vy j cap plus d by dt of vz k cap. Okay, so the rate of change of the x component of velocity, basically we can write it as x component of acceleration. So ax is equal to d by dt of vx. Okay. Similarly, d by dt of vy would be equal to ay, or the y component of acceleration, d by dt of vz, which is nothing but az k cap. So here also, if you observe, the x component of acceleration, or acceleration component parallel to the x-axis, only depends on how the velocity component parallel to the x-axis changes. Okay, so the x component of acceleration is independent of the motion of the body parallel to y or z axis. Okay, so this is about the basic, the relations between them. Okay, so one small point I will repeat again, which is very important. So the motion of the body, okay, that is the displacement parallel to x-axis, or velocity parallel to x-axis, acceleration along x-axis, are related among each other, but they are independent of the quantities along y or z axis. Or I can say something like this: displacement parallel to the x-axis would only depend on the x components of velocity and acceleration, or the displacement along x-axis is independent of velocity and acceleration along y or z axis. So this point is very important when we proceed solving with the problem. Okay, so let us try to do one simple problem in order to understand what I just said earlier. Okay, so let us take something like this. Let's say a particle was moving such that its position vector is changing something like this: 3t I cap plus 4t square j cap. So here the particle position is represented as a function of time t, okay, and as a vector quantity. Now if you see, the particle does not have any component of z component of the position, so which indicates that it's basically moving in xy plane, because it has only x and y components of the position. Okay, so now my first intention is to find how the velocity and acceleration varies with time t. So velocity would be d by dt of 3t I cap plus 4t square j cap. So if we differentiate it, d by dt of 3t would basically be 3i cap, d by dt of 4t square is 8t j cap. So this is how velocity varies with time. Let's assume we were taking the physical quantities in SI units. So though I haven't represented the units, let's say we were taken in SI units itself. Then as you can see here, look at x and y components of the velocity. Here x component of velocity is basically 3. It's not dependent on time. So basically what I can conclude is, so corresponding to its motion parallel to the x-axis, velocity is constant, which means the x component of acceleration is basically 0. And if you look at the y component of velocity, it's proportional to time, it's dependent on time. So what I can conclude from that is that the acceleration, the velocity of the body parallel to the y-axis is changing. So definitely parallel to the y-axis it has acceleration. So if I differentiate this once again, I would basically be getting acceleration. So I would get acceleration is equal to d by dt of v bar, which would be equal to, if you differentiate it further, once again, velocity d by dt of 3 as a constant quantity, so you would get 0 I cap plus d by dt of 8t j cap would be 8 j cap. So your acceleration has only y component and x component of acceleration is 0. Now let's say our intention is to find the displacement of the body after certain amount of time. Let's say our intention is to find the displacement in 8 seconds. Okay, displacement in the first 8 seconds. Okay, let's write it something like this. If I write 8 as a subscript, you might misunderstand that it's the displacement in the 8 seconds. So in 8 seconds, if we want to find the displacement, so what we would be doing, displacement in 8 seconds, we can write sx I cap plus sy j cap, where sx and sy are the x and y components of displacement in that 8 seconds interval. See here also, even in this discussion regarding motion in a plane, the kinematic equations are still valid provided the acceleration is constant. So here what we would do, we will use those kinematic equations separately for motion along x-axis separately and for motion along y-axis separately. So I can write the displacement parallel to the x-axis would be uxt plus half ax t square. So here sx is the displacement parallel to the x-axis, ux is the initial component of the velocity, or the component of velocity at t is equal to 0, okay, along x-axis, and ax represents x component of acceleration. So since our intention is to find the displacement along x-axis in 8 seconds, okay, first if you look at the velocity is constant at t is equal to 0 also, it would be equal to 3 units into t would be 8 plus, as we already discussed, x component of acceleration is 0, this would come out to be 0. So since the component of velocity along x direction is not changing with time, if you see, it's basically something like velocity into time. So the displacement parallel to the x-axis is basically 24 meters. Then look at, let's calculate y component of displacement in the same amount of time. Sy is equal to uyt plus half ay t square. So initially at t is equal to 0, the y component of velocity would basically be 0. As you can see, it's 8t. If you substitute t is equal to 0, we'll get initial y component of velocity as 0 plus, and as you can see, the y component of acceleration is constant here. So hence I can use these kinematic equations for calculating y component of displacement. If y component of displacement was varying, or if it was dependent on time t, then in that case it doesn't corresponding to the uniform accelerated motion. In that case we can't use the kinematic equations. So ay would be 8 into 8 whole square. Square is not visible here. So we get 64 into 8, 4, I think it would come out as 256 meters. So we can write the total displacement during that 8 seconds interval as 24 I cap plus 256 j cap. Okay, that would be in meters. Since I told you I'm taking things in SI units. This is how we can proceed. Okay. Now let's continue to discuss the projectile motion, where projectile motion basically corresponds to motion in a plane. Okay, let's discuss briefly about it. Let's say this was the ground. So we projected a body with speed u, making an angle theta with the horizontal. So it would basically kind of follow a parabolic path. So that we already proved in the first PU that a projectile, once it's projected, so it would basically follow a parabolic path. Okay, we derived the equation of the motion of that projectile. So from there we concluded that it follows a parabolic path. So once you project the projectile, okay, here we can resolve its velocity into two components. The component parallel to the ground, or the horizontal component, would be u cos theta. Component perpendicular to the ground would basically be equal to u sin theta. So once you project it, the only force that would be acting on it would be the gravitational force, which would be vertically downwards. Okay. For in day-to-day life, for the small speeds with which we project a body, the body generally kind of rises to small heights. So for those small heights, the variation of g can be neglected. So we can assume g is a constant, or the gravitational force is constant on the body. And we are not considering air resistance here. Considering air resistance would make the things very complicated. And since the body has only acceleration along vertical direction, okay. So as we discussed earlier, so let's consider x-axis and y-axis like this. Or in this case, I can say the body only has the y component of acceleration, but whereas x component of acceleration is basically 0, because there is no force acting along x direction or in the horizontal direction. So hence x component of acceleration is 0. And if you look at y component of acceleration is minus g, it's constant throughout its motion. So we can basically use kinematic equations in this particular case. Okay. So, and since there is no x component of acceleration, so we can conclude that the x component of velocity of the body will not change with time. It would remain the same, u cos theta, all the time, both in terms of magnitude as well as direction. But if you look at y component of velocity, it would basically change with time because of the acceleration. Okay. So as it goes up, the y component of acceleration would basically decrease. At the highest point, y component would be 0. So hence the particle will only have the horizontal component of velocity, which is u cos theta. So at the highest point, remember this, so many of you make this mistake. At the highest point, velocity is not 0. Vertical component of velocity is 0. Okay, the particle will still have horizontal component of velocity. But in the in the previous section when we discussed motion in a straight line, if a body is projected vertically upwards, it only has vertical component of velocity. It didn't have any horizontal component of velocity. So that's why we said velocity was becoming 0 at the highest point, because the vertical component would definitely become 0, which is its total velocity. But here that's not the case. It has a horizontal component of velocity. So at its highest point, the velocity will not become 0, it will have a horizontal component of velocity. Okay. So vertical component of velocity would basically decrease, would become 0 at the highest point, then as it goes down, it basically again increases. Okay. So now I hope you remember the derivations related to the range, time of flight, and the maximum height reached. So this would be the range and this would be the maximum height, and time taken to go, let's say it was projected from point A and let's say it hits the ground at point B. So the time of flight, that is the total time for which it's been traveling before it hits the ground again, which is 2u sin theta by g, or we can also write it as 2 into uy by g. So where uy represents the vertical component of the body at the moment of projection. Then what about the maximum height reached by it? So the maximum height reached by it is basically u square sin square theta divided by 2g. or we can also write it as u sine theta whole square divided by 2g, which is equal to uy whole square divided by 2g. That's the maximum height, reached by the projectile. Then what about the range? The range is given by, the range as you basically see, it's a horizontal component of displacement of the body as it goes from A to B. The range would be the horizontal component of velocity. Horizontal displacement only depends on horizontal component of velocity, and as you can see, it's constant. The time taken to go from A to B, time of flight, which basically gives you u cos theta into 2u sin theta by g. So we can basically write it two ways: 2 into ux into uy by g. Ux is u cos theta, uy is u sin theta. U I'm basically using for initial velocity. Ux and uy are initial x component of velocity and initial y component of velocity. Or we can also write it as u square sine 2 theta by g. So this is the range of that particular projectile. Okay. Now let's discuss a few points based on which they can basically frame a question. Okay. So first thing regarding the range. Okay. So range, if you look, range is given by u square sine 2 theta by g. So here the range depends on the value theta. So depending on, even if you project two bodies with the same speed u, but if the angle of projection is different, theta is different, range would basically be different. Okay. So now our interest is to find the value of theta, okay, for which the range would be maximum for a given speed. Okay. So if r has to be maximum, so that implies sine 2 theta has to be maximum. So sine 2 theta has to be maximum. The possibility is 2 theta has to be 90 degrees or theta is equal to 45 degrees. So if you wish to project a body with a certain speed and you wish the range to be maximum for that speed, so we must project it at an angle 45 degree with the horizontal. For that angle of projection, the range would basically be maximum. And then for complementary angles like theta degrees and 90 minus theta, okay, the range would be same. You can substitute these values and you can just check. Okay, so they can ask a question, simple question based on this point. Okay, so for theta, 90 minus theta, provided in both cases the speed of projection is the same. Let's say something like this. In one case you projected the body with 30 degrees and in other case you projected with 60 degrees. Okay, with the same speed. Then in both cases the range is same, but the height need not be same. The time of flight also need not be same. Keep that in mind. Okay, only the range would be same. Okay, now let's proceed to discuss a few points further. Okay, now sometimes what they do, okay, they might ask you a question something like this. Okay, the body is projected with a velocity u, making an angle theta with the horizontal. Now their question might be something like this: at what minimum time after projection velocity makes angle alpha with horizontal? Okay, velocity makes angle alpha with horizontal. To find this, what we are going to do, we are going to use the fact that throughout its motion the horizontal component of velocity will not change, it would remain the same. So that we will be using to our advantage. Okay, so now I projected it with velocity u, making an angle theta with horizontal. The horizontal component of velocity is given by u cos theta and then u sin theta. So let's say after certain time t, the velocity v is v, making an angle theta with alpha with the horizontal. Now we wish to find the time t. Here, if velocity is v, the horizontal component of velocity would be v cos alpha. Vertical component of velocity would basically be v sin alpha. If you observe, at both points, horizontal component of velocity have to be same. So v cos alpha must be equal to u cos theta, or we can basically write, okay, v is equal to u cos theta by cos alpha. But this is what we are interested to find basically. We are interested to find the time after which it would make an angle alpha. So see here, the vertical component of velocity will keep changing with time. So if initially it was u sin theta, now let's say after time t, its vertical component of velocity is v cos alpha at the moment when its velocity makes an angle alpha with horizontal. Then what I can write? V sin alpha is equal to, I'm using v is equal to, vy is equal to uy plus ay into t. I'm using v is equal to u plus at for the velocities and acceleration along y direction. So v, we already got it as u cos theta by cos alpha into sin alpha is equal to u sin theta minus gt. You simplify this, I mean theta, alpha and u are a part of the question. So the time t that you get is the time after which, okay, its velocity would make an angle of alpha with the horizontal. Okay, so sometimes they will ask problems based on the fact that the horizontal component of velocity will not change. Okay, next, let's focus on a little bit about equation of projectile. Equation of projectile. So the equation of projectile is given by y is equal to x tan theta minus gx square by 2u square cos square theta. Okay. So here, what is x and y? Okay, I would represent it in the form of a graph. So imagine we take, let's say we projecting a body from the ground. Let's say x-axis is parallel to the ground and it coincides with the ground. Okay, this is the ground basically, x-axis. Let's say we project the body from origin. Okay, let's take y-axis. Y-axis is a line perpendicular to the ground. So if we project it with the speed u, making an angle theta with horizontal. So we projected it at t is equal to 0 from the origin. So it basically follows parabolic path and hits the ground. So as it moves in a path, okay, it's, I mean, x and y coordinates would basically be changing with time. So at some random instant of time, x and y coordinates are given by x comma y, and the relation between y and x is given by this. Okay. So basically, since this is something like y is equal to ax plus bx square, which is the general form of a parabola, so we can conclude that it follows a parabolic path. Okay. Now we also concluded that you see similar point in the case of the motion of a charged particle in a uniform electric field. Okay. One main interesting connection between this motion and motion of a charged particle in uniform electric field is in both cases, I mean, the acceleration is constant. Okay, so if it's projected making certain angle with that direction of that acceleration, the particle basically follows parabolic path. Okay. So this same relation we can write it in a different way. If we take x tan theta common, x tan theta of 1 minus g x divided by 2 u square cos square theta into tan theta. Okay. So here in the denominator we have cos square theta into tan theta. Cos square theta into tan theta would basically come out as sin theta into cos theta. So you can write it as x tan theta of 1 minus gx by u square into, you would have 2 into, this is sin theta into cos theta, which is sin 2 theta. So we would have x tan theta of 1 minus x by u square sin 2 theta by g, which is nothing but range. So we can also write it something like this. Sometimes this problem would basically, this expression of yx connecting r would help us in solving the problems. Okay, and this is the equation of projectile. Let's try to discuss the projectile motion from top of a building. First, let's discuss the horizontal projection from top of a building. Then we will discuss the oblique projectile from top of a building. Horizontal projection. So all things I am doing a bit briefly, not in detail. Let's say we have a building of height h. So we were standing on the top of the building. Then what we did, we took a body and we projected it horizontally. We have given it some velocity. Let's say that velocity magnitude is given by u, and that velocity direction initially was parallel to the ground or horizontal. So basically here also we can prove it follows a parabolic path. Now our interest is to find few things, okay, time taken to reach the ground and all those things. Okay, so first thing here, since it's projected horizontally and there is no acceleration along horizontal direction, acceleration would basically along vertical direction. So the particle's horizontal component of velocity will not change with time. So at any point in its path, okay, as it falls down, the horizontal component of velocity would all the time be the same, which is nothing but u. But its vertical component of velocity, which is initially 0, would keep on changing because of the acceleration of that particular particle. Okay, now acceleration is given by minus g. First let's try to find the time taken by the body to reach ground. Okay, so if it goes, let's say projected at point A, it hits the ground at point B, this would be the actual displacement of the particle. So we can write it as displacement parallel to x y direction, and the displacement parallel along x direction. You see, as we discussed earlier, displacement along y direction depends only on along the velocity along y direction and acceleration along y direction. Okay, so first let's find time taken. So if the particle goes from A to B, the y component of displacement would basically be h, and y component of acceleration would be minus g, and initial y component of velocity was 0. So let's use this equation, sy is equal to uyt plus half ayt square in order to find the time taken for that displacement. Minus h is equal to 0 into t plus half into ay is minus g into t square. We would basically get t is equal to root of 2h by g. So that's the time taken by the particle to go from A to B. Okay. Then the next thing, one small point. If you observe this time taken is same as time taken by a freely falling body from height h. The both relations are the same. The reason for this is in both cases the body initial y component of velocity was 0, and we want time when it undergoes a vertical displacement of h. Okay. Now let's continue further in order to find this thing, the range. What about the range? So the range, we know, as you can see here, it's a horizontal component of displacement. Along horizontal direction there is no change in basically the velocity, it remains constant. So I can write x component of velocity into time taken to reach the ground. x component of velocity is basically u, time taken to reach the ground is root of 2h by g. Now let's say our next interest is to find the velocity or the magnitude of velocity of the body at point B. So if you look at point B, this is point B. So it will basically have two components of velocity. One is horizontal component would basically be u only, but vertical component of velocity is what I'm interested to find. I can write vertical component of velocity as uy plus ay into t. So when it goes from A to B, at A initial y component of velocity was 0, y component of acceleration was minus g. T represents time as it takes to go from A to B, during which its velocity was increasing. It should be root of 2h by g, which is equal to minus root of 2gh. So this relation is also similar to what we have discussed in the case of freely falling body. So it would have a vertical component of root of 2gh. So the resultant of these two, okay, would give us the magnitude of velocity of the body. So v would be root of vx square plus vy square, which would be root of u square plus 2gh. So this is the magnitude of its velocity at point B, I mean just before hitting the ground. Now if you are interested to find what angle its velocity would make with the horizontal, the tan theta is given by, if you see in that triangle, opposite divided by adjacent. So that's how you can find the angle theta. Okay. Now let's discuss a little bit regarding the, what do we say, the oblique projectile from top of projection from top of a building. So if this is a building that we have of height h, let's say, we took a body and then we projected it with the speed u, making an angle theta with horizontal from top of the building of height h. Okay, now, so once you project it with the speed u, making an angle theta with horizontal, this is theta. The horizontal component is given by u cos theta, vertical component is given by u sin theta. Okay, then it follows a parabolic path and hits the ground somewhere over here. So we wish to find the same things that we have calculated earlier, that is the time taken, the range and the velocity. So I wouldn't be doing the detailed calculations here, but I will explain you the math behind the calculations. First, if you look here also, the x component of acceleration is 0. As the body goes, let's say this is point of projection A, this is the point where it would strike the ground. This would be the displacement. The displacement, we can resolve it into two components. Vertical component would be y, sy. The horizontal component would be sx. So sy would basically equal to minus h, minus indicating that that component of displacement is in the downward direction. So first my interest is to find the time taken by the body to reach the ground. So I would use this relation, sy is equal to uyt plus half into ay into t square. Sy, initial y component of this, as it goes from A to B, the y component of displacement is minus h. Uy represents initial y component of velocity, which is u sin theta, that too positive, because as you see it was in the upward direction. Okay, so suppose let's say the same projectile was projected with the speed u, making an angle theta horizontal from the top of the same building, then in that case initial y component of velocity u sin theta but in the downward direction, then in that case we must consider minus here, okay, to t. So t is the time taken by the body to reach the ground, half into y component of acceleration would be downwards, which is t square. So we would get g by 2t square minus u sin theta into t minus h is equal to 0. So basically we got a quadratic equation here. Okay, so if we use t is equal to minus b plus or minus root of b square minus 4ac if we would get it as 2gh divided by 2 times g by 2, which is g. Okay. So since the time that it takes is basically positive, okay, here two solutions is possible. One is plus with the other is minus. So the time that you take must be positive. So the time taken by it to reach the ground would be u sine theta plus this would be the time taken plus root of u sine theta whole square plus 2gh divided by g. So this is what the time taken by the body will be when it reaches the ground. Now if you are interested to find that the range or the horizontal component of displacement, that would be horizontal component of velocity u cos theta into time taken to reach the ground, or you can write it as u cos theta into t is nothing but u sine theta plus root of u sine theta whole square plus 2gh divided by g. So this is what the range would be. Similarly, you can also find the velocity of the body as it reaches the ground as we proceeded earlier. Okay, I hope you understood this. Let's discuss briefly about projection on inclined plane. Briefly, I'm not going to go into detailed explanation, and then we will wind up this session. So let's say we have an inclined plane, something like this. Let's say which makes an angle theta with the horizontal. Let's say I projected a body with a speed u. Okay. So what I did, I projected it with the speed u, making an angle alpha with the horizontal, not horizontal, with the inclined plane. Now it would basically go something like this and hit the inclined plane somewhere over there. Okay. So now what we will do, let's say we wanted to find the time after which it would strike the inclined plane. That's our main intention. Okay, time after which it would strike the inclined plane. Let's say we projected it from point A, it strikes the inclined plane at point B. Okay, two things I will try to help you to calculate. The first thing is time it takes to go from A to B. Next thing, the displacement from A to B. So to make the situation easier, what we'll do, we'll assume one of the axes parallel to the inclined plane and the other perpendicular to the inclined plane. And I'll tell you the reason why I made this choice of the axis. So once we imagine axis, now let us resolve the vector that we have into parallel and parallel to those axes. First, u was making an angle alpha, then we can resolve its components are going to be u cos alpha parallel to x-axis and u sin alpha parallel to y-axis. And acceleration would basically be downwards, that is g. So it would make an angle, okay, theta with the vertical. So it's the component parallel to the y-axis would be g cos theta, parallel to x-axis would be g sin theta. So I can write here x component of velocity initially is plus u cos alpha, okay, and the x component of acceleration initially is minus g sin theta, minus because it's anti-parallel to x-axis. What about the initial y component of velocity? U sin alpha, but initial the y component of acceleration is basically minus g cos theta. The first thing we wish to find is the time taken by the body to reach ground. So if it goes from A to B, so once it goes from A to B, okay, it would have this would be the displacement. That displacement, if you see, is parallel to the inclined plane or parallel to x-axis. So if it goes from A and after a time t it reaches B, let's say after a time t it reaches B, so in that time capital T, the total y component of displacement would be 0, because you see the displacement is parallel to x-axis, so it doesn't have any y component of displacement. I will use this fact in order to find the time taken to go from A to B. Okay. So Sy is equal to 0. So since if you observe x and y components of acceleration here, okay, so both are not dependent on time, or both components of acceleration are constant. So which means that the accelerations are constant, so I can use the equations corresponding to the uniformly accelerated motion. So I can write Sy as, just a minute, Sy can be written as uy t plus half ay t square is equal to 0, where t represents time taken to go from A to B. Uy, we got it as u sin alpha into t plus half into the y component of acceleration is minus g cos theta into t square is equal to 0. Or if I take t common, u sin alpha minus g cos theta by 2 to t is equal to 0. So we can write u sin alpha minus g cos theta by 2 into t is equal to 0, or we would get t as 2u sin alpha divided by g cos theta. So this is the time after which it would basically strike the inclined plane. Okay. Now the next thing I was interested to find was, so the distance between A to B, or this, what would its displacement be in the time when it strikes the inclined plane. So basically we want to find the distance between A to B, which would be the total displacement during that time t, or which would be the x component of displacement. Okay, so that x component of displacement would be ux t, just a minute, plus half ax t square, which would be, so the initial x component of velocity, we got it as u cos alpha, t is basically 2u sin alpha by g cos theta, plus half into ax is given as minus g sin theta into t is given as 2u sin alpha divided by g cos theta whole square. Simplify this relation, you would get the displacement, okay, of the body parallel to the inclined plane. That's it for the video. In the next video we'll discuss briefly about circular motion and relative velocity. Once we do discussion about that, I will discuss a few problems related to this chapter. Okay, bye bye.